Hi, good morning, everyone. I hope you're all doing well out there. Today we will be talking about the icy moons of Jupiter and a little bit about Saturn's icy moons. We'll take an in depth look at the four Galilean moons of Jupiter, and we will talk a little bit about Titan and its atmosphere. All right, let's go ahead and begin. So, the innermost moon of the four Galilean moons, so this is the innermost moon, is named Io. Sometimes it's pronounced Io. Now, this one has way too much tidal heating. And I say too much because it has no liquid water. It's way too hot for that. You can see that it's heated up so much that there are giant volcanoes going off here. The whole surface, you can see the red colors, the orange colors. That's primarily sulfur compounds. Remember, sulfur dioxide is one of the gases that comes out of volcanoes, and that sulfur dioxide reacts with sunlight on the surface of Io, and it forms a whole variety of different sulfur compounds here. It is the most volcanically active body in the solar system, which is kind of interesting, but doesn't really help us out when it comes to astrobiology and looking for life. So that's about all we're going to say about Io. And we're now going to move on to Europa. This is the best candidate for life. This is the second moon out. And some things I would like to point out here before we get going is that there's a couple of different types of terrain here on Europa. You can see what's known as smooth terrain and what's called chaotic terrain. Oops. And these are different regions. And one thing is that this is the smoothest body in the solar system. That means something's continuously resurfacing it. We can see one little crater here, but that's about it. Remember that this might be an old crater over here. Remember that the older a surface is, the more craters there are. So there must be something resurfacing this. We think that's probably cryovolcanism. You can see here in this picture here, we have these geysers coming out of volcanoes. So these are volcanoes of ice, and we think that that is completely resurfacing it. So there's all this icy material that's coming out of these cracks. You can see the cracks all over the place here on the surface. And as stuff comes out of these cracks and vents, it then settles on the surface and creates a nice new fresh layer all the time. So that's probably helping to resurface this. And this is all happening because Europa has just the right amount of tidal heating. Just enough so that it probably has a global ocean. And that ocean is probably 60 to 150 kilometers thick. That's a pretty thick ocean, and it's covered by a layer of ice. You can see that over here in this picture. This layer of ice is probably 20 to 25 kilometers thick. Yeah, one thing about this ocean is it's probably salty. And so it's helped keeping it liquid, maybe providing some nutrients for life, but very, very interesting object. You might be wondering about the orange color here, if this is water ice on the surface. We think all of this orange material are called tholins. These are large organic molecules. There's probably small organic molecules leaking up through these cracks, and as those react with the UV light from the sun, it's pretty weak out here, but there is some ultraviolet light, that those react and form larger and larger organic molecules. So this is really exciting for life. We have an abundant amount of liquid water. There's obviously heat there. There is a large amount of organic materials, so pretty exciting. Best candidate so far for life. I forgot to label that. I'll put that on there, ice layer. So how do we know that there are oceans under Europa's surface? So there's really three pieces of evidence here, and I'll just highlight those real quick. We saw that there is repaving on the surface. We talked about that. It's the smoothest overall body in the solar system. Deviations of less than a kilometer or so no mountains, no deep canyons, and we think that's probably from repaving. Again, there's no craters to be seen. What's covered those up? We think this is cryovolcanism. This is actually evidence for an abundant source of water underneath. It means there's heat. It means there is liquid water down there. Also, that chaotic terrain that we talked about, I pointed out a little bit on the previous slide. You can see that down here. So this is a close-up of that terrain. And what you'll see is that I actually believe this is from Earth and this is on Europa, that these two terrains look very, very similar. And similar enough that people think that it's the same processes going on, that we have ice sitting on a layer of water. That ice is continually moving around a little bit. It's bending and flexing and cracks are opening up. And it looks very much like the frozen Arctic ice pack, where we also have a layer of ice sitting on water that's moving around, bending and flexing. And morphologically, it looks nearly identical. So good evidence that that's what's going on there. And the last one is looking at the magnetic field of Europa. And it's not static. It doesn't sit still. It changes. And the only way to explain the shape and the behavior of the magnetic field is that it's interacting with a salty, convective ocean of water. I say convective, I meant conductive. So magnetic fields react with charged particles. When salts dissolve in water, they become ions. And so if there is a thick, salty ocean, those ions, the salt ions, will interact with the magnetic field. So good three pieces of evidence. Again, strong evidence for a global subsurface ocean of salty water. So we know all three of those things point to having a global ocean. All right, so here's a question for you guys. Europa likely has a large liquid ocean beneath the icy crust. Why do scientists think there's a low probability that widespread abundant life doesn't exist in this ocean? All right, well, the correct answer here is C, in that there isn't much available energy. Remember, one of the key ingredients for life is energy, one of the three key ingredients. And we think that the ice is too thick and the sun too weak for photosynthesis. You can just fit that in there. And remember, that's one of the main drivers of life and energy here on Earth, are photosynthetic plants and bacteria. So without that at the bottom of the food chain, you couldn't have abundant life sources. Now, it isn't to say that you couldn't have small colonies of life, especially down at the bottom of the ocean. So let's go through some of these and kind of help explain that. So organic molecules for life are actually readily available. So in this is actually true that there are. Remember, we just talked about the picture of Europa and those orange features, the cracks, and that those orange features were organic molecules. So we think that all of the other two ingredients are here. We have liquid H2O plus organic molecules, but there's not enough energy. Although, like I said, there could be energy down in the core, down at the bottom of the ocean. So ongoing tidal heating and maybe some radioactive decay is powering volcanism, but it's not dangerous. This volcanism is actually good for life. It might support colonies of life, like the black smokers at the bottom of our own ocean. And this is a source of energy, both heat energy and chemical energy. Reactions with Jupiter's magnetic field might destroy life. It turns out that there are reactions with the field, but it may actually enrich the ice with hydrogen and oxygen, both key ingredients for energetic reactions. So C is the best answer here. A, B, and D all had pieces that were correct, but pieces that made them wrong. So to just sort of sum that up again, we have two of the three ingredients here, liquid water and organics, but the third ingredient, not enough energy, is probably the problem here. All right, well, we still have two moons of Jupiter to go through real quick. We have Ganymede. This is partially active, and I mean geologically. Geologically. You can see that here, that there's two types of terrain. There's this old, heavily cratered terrain here and here, shown here in this picture, and there's also much younger, smoother terrain, like in this region, all through here, all this stuff, and you can see that smooth terrain over here with the grooves. So there's some activity on the surface, not much at all. We think that this is because there's not much tidal heating here. There's a little bit, but it's farther from Jupiter. Also, this is a much larger body. I don't know if that affects the tides very much, but this is the largest moon in the solar system. And it may have a deep ocean, but covered in thick ice layer. So it means that there could be life there. But it would be very deep in the planet. And so not a good place for us to look, not to say that it isn't there, but more difficult than finding it at Europa, where those cracks penetrate all the way through the surface, and the orange gunk indicates that there's processes bringing water up to the surface. All right, the last moon here is Callisto. This is the farthest moon out, so this is the farthest Galilean moon from Jupiter. We can see here that it's a very old surface. We can tell that by the amount of craters that are there, and this is because there are no resonances here. and so almost no tidal heating. And what little it would get from Jupiter is pretty weak because it's so far out. There's also only partially differentiated. Remember, this is the process by when the planets form, they heat up enough that the rock, they fully melt, the rock goes to the center, and then water and ice go to the surface. The denser layers go down, and so that means there's probably not a thick ice layer as thick as on the other Galilean moons. So there's obviously some, but not a thick layer. And yet, despite all this, evidence indicates that it does perhaps have a subsurface ocean. And I'll just put a question mark on that. We don't really know whether or not that ocean really exists. The evidence isn't quite as strong as at Europa, but it's an icy body, and so it very well could be. The density of this body indicates that it's about 50% rock and 50% ice, which is true for most of these outer Galilean moons, other than Io, which has been heated up so much it's lost all of its ice. So that's the Galilean moons, the 4 largest moons of Jupiter. Those are the only moons of Jupiter we're going to look at. And now we're going to move over to Titan a little bit. This is one of Saturn's moons. The first thing you might see in this picture is that it has a very thick atmosphere. And it's really the only moon in the solar system with an atmosphere. That's very unique about it. It does have a similar density to Callisto. Which, remember, means that it's about 50% ice and 50% rock. And this thick atmosphere it has, the atmospheric pressure, which tells us how much atmosphere there is about the same as Earth. It's actually a little higher, but it's got a different composition than Earth. It's about 90% nitrogen. And 2, Earth's is about 60% nitrogen, 70% nitrogen. And the rest is carbon dioxide and hydrocarbons. Those are things like methane, which is CH4. So we call these hydrocarbons because they're made of carbon and hydrogen. Acetylene, which is large enough I'm going to not write out the whole thing, and hydrogen cyanide. So basically organic molecules. If you're wondering, this little moon in the back is another moon of Saturn called Tethys. And you can see how crisp and sharp its edge is. It has no atmosphere. I thought this was a nice picture because it sort of contrasts this moon that has an atmosphere with one that doesn't. It's got this beautiful orange haze color to it, that orange haze. This is often referred to as just the haze or hazy layer, probably made out of organic molecules. So where did this thick atmosphere come from, or sort of what its features? This is a pretty confusing picture, and I'm just going to draw your attention to some of it. So you can see down here and here that the surface is made of water and ammonia. So it's cold enough for ammonia to freeze out here, and that's NH3. Now, for impacts, whatever reasons, this ammonia evaporates, and that puts the ammonia in the atmosphere. So ammonia evaporates, it reacts with ultraviolet light, and it leaves the nitrogen behind. So we think that's where the nitrogen comes in the atmosphere. There's also methane in the atmosphere. So methane and methane and nitrogen clouds, because that's what's in the atmosphere. Those things condense out and form clouds. So we get these methane, nitrogen clouds, which is from the ammonia forms that, plus ultraviolet gives us nitrogen. The hazes up here at the top, those were the orange hazes in the picture. The hazes are made from UV plus the methane. That's the CH4, remember? That's also... Now, one of the big problems here is that this methane should be lost to space unless something is replenishing it. And we see that down here, and there's good evidence for this now. We've actually taken pictures of these. There are methane lakes here. So we think that the methane in the atmosphere is coming out of the methane lakes. Other than that, we don't know where it could be coming from. Something has to be replenishing the lakes, but we do have a whole methane cycle here. It could be that some of this ingredients for the methane is coming out of the volcanoes. Some of the methane is then being lost to space. Some of it condenses out into these clouds and rains back down, and then it evaporates. And so we have a whole methane cycle here, just like the water cycle on Earth, where we have evaporation and condensation and rain. Rivers form into lakes, and then those evaporate. We get clouds, rain, and the cycle continues. So very complex atmosphere, pretty interesting place. Now, the last thing I'm going to leave you with here is a writing prompt. Titan is only slightly smaller than Ganymede, but it is the only moon with significant atmosphere. So what are the two explanations for Titan having an atmosphere, but Ganymede not? So push pause and write this out on your own for a moment. All right, so it turns out that the two reasons, the first one is that methane condenses at lower temperatures than water. Thus, Titan formed with more methane because it was farther out in the solar nebula than Ganymede. So remember the solar nebula? That's our nebular hypothesis of how the solar system formed, and that it was colder and colder and colder the farther we went out. That's why in the inner part only rocky planets formed, because only rocks could condense out. And as we get farther out, the gases could condense out. And as we get farther and farther, we get more and more stuff condensing out. And so it could be that Jupiter and Ganymede formed in a part of the solar system where it wasn't cold enough for a lot of methane to freeze out, and yet Saturn and Titan were at a region where a lot more methane was freezing out because it was colder, and so that's why it ended up with more. The second explanation could be a removal process, in that comets move slower, farther from the sun, thus impacts with Titan would have less energy than those at Ganymede. So if they have less energy, they're gonna remove less methane from the atmosphere. So comets would have evaporated less methane at Titan than Ganymede. So again, two explanations for the difference in Titan and Ganymede with respect to Titan having an atmosphere. The first one is a formation explanation, that Titan simply formed with more methane because it was colder where it formed, so more of it can condense out. And the second idea is that maybe during late heavy bombardment, when early part of the solar system, when there were lots and lots more impacts, that comets out there were moving slower, and so when they did hit Titan, they didn't get quite as hot. They didn't release as much energy as they would have at Ganymede, and so there was just more evaporation going on, and so at Ganymede, and so Ganymede lost more of its methane. And yeah, so that's it for those two. We're at the end of our lecture for today, so thank you very much. And I should have all of those exams graded by Friday, by the end of today. All right. Thank you. Take care. Be safe.